Alright, so we're going to talk really quick here about the question of why are some compounds more acidic than others. Now it turns out there's a bunch of different reasons for this. There's in fact 4 main reasons. We're going to go through them each in turn. The first one is so-called element effects, and by element that means the atom that's directly connected to the hydrogen. If you're talking about binary acids like these, binary acids meaning hydrogen and one other element, then the identity of that element determines the acidity of your compound. Alright, so we're going to look at this in terms of the periodic table. We can talk about what happens when you go down a group. This is the halogens here, chlorine, bromine and iodine. In fact, fluorine is up at the top of the halogens, so we could say fluorine, chlorine, bromine, iodine. In fact, I'll add these on here. So one question would be, well, what's the relative acidity of these acids? Well, you probably know these to be strong acids: hydrochloric acid, hydrobromic, hydroiodic acid. You've also heard of HF, hydrofluoric acid, and although if you've watched Breaking Bad you'll have seen the things that HF does to a body, it's weaker an acid than each of these other 3. So when you go down a group, we're going down group 7 here, fluorine's at the top, iodine's at the bottom, the larger the element, or the less electronegative it is, because fluorine's the most electronegative, iodine is the least here. Going top to bottom, going down a group, the acidity of your acid is going to increase. In other words, going down this group, the strength of the acid is increasing. So therefore HI is the strongest acid between HI, HBr, HCl and HF. And HF out of those 4 is the weakest acid. Alright? So HF is the weakest acid, HI is the strongest acid. So the point is, going down a group, whether it's group 7 or whatever, any group, going down a group, the acidity will always increase going down if you have a binary acid. Now remember, the concept of weakest and strongest is all relative. Out of these 4, HF is the weakest acid. When we look at these 4 elements though, carbon, nitrogen, oxygen and fluorine, this is one of our periods going left to right. The trend is actually kind of opposite. So when you look at these 4 compounds, methane, ammonia, water and hydrofluoric acid, well, only one of them has the word acid in it, which should tell you which is probably the most acidic. The fact is, as you go across a group left to right, as the electronegativity increases, so does the acidity of the acid. Therefore, going left to right across here, acidity increases. Alright? In other words, HF is the strongest acid out of these 4, because fluorine's the most electronegative element out of these 4. Carbon's the least electronegative, so CH4 is the weakest acid. Ammonia is next, so it's the next weakest acid, then water, and then HF. So just to summarize, when you're looking at elements going left to right across the same group, the same period in the periodic table, acidity increases left to right. The higher the electronegativity, the stronger the acid. When you're going down a group, size is what's important. The bigger the atom, the better the acid it is. In other words, that's why when you go down this group, HF's the weakest acid, HI is the strongest acid. So that's so-called the element effect. Another effect that influences acidity is called the inductive effect. Inductive meaning something pulling on something else. So take a look at these 4 compounds. They're all similar in that they all have an OH. This is an alcohol. And the acidity portion here is this hydrogen that can come off. Notice how all 4 alcohols have exactly the same hydrogen there. The question is, in which case is the hydrogen going to come off the easiest? Which of these 4 compounds is the most acidic? Well, take a look at the molecules and see what's different about them. This one just has carbon and hydrogen. Notice how this one has a chlorine there on that second carbon. Now, from what I'm sure you remember, chlorine is more electronegative than hydrogen. So what that means is the chlorine is going to pull electrons this way through the molecule and make this hydrogen easier to come off. Alright? And the reason why that happens is, if we draw this product out, alright, when that hydrogen comes off, every time you're looking at whether if a compound's more acidic than something else or not, don't worry about these hydrogens. That's just a function of the software that I have here. It's just screwing with me. Bloody software. If this hydrogen comes off, we have this negative charge on this oxygen here. Doesn't particularly like it. The chlorine pulls electrons towards itself because it's electronegative and eases the burden on the oxygen. Alright? So the more groups you have that are electronegative, the easier the hydrogen is going to come off. So this guy here with no halogens on it is the weakest acid. Now when we compare this guy and this guy, now what's the difference between these two? Of course the big difference is, well, you know what, I noticed this one has one too many carbons in it. Well, anyway, the fact is, the more electronegative atoms you have, I really should have done this with just 2 carbons rather than 3, so my bad for that. The difference though here is 2 halogens versus just 1 mean that the acidity is going to be higher in this case because I've got more electronegative atoms pulling electron density away from my oxygen when I lose that hydrogen. Alright? Now when we go up to here, I want you to compare these two. We can't compare these two because there's 2 halogens here and only 1 here, but we can compare these two. What do you guys remember? Which element is more electronegative? Is it chlorine or is it fluorine? Well, it's fluorine. That's the most electronegative. Therefore the fluorine is going to pull on the electrons stronger than the chlorine is, and what that means is if I draw out this conjugate base in exactly the same way that I did before, what you're going to find is that because the fluorine pulls more strongly, that makes this O- happier because the fluorine is pulling the electron density away from it and the negative charge isn't wholly on the oxygen anymore. This conjugate base is more stable than this one, therefore this is the stronger acid. Alright? So summary here is electronegative elements make compounds more acidic, more of those electronegative elements make a compound more acidic still, and elements that are even more electronegative do that same job. Alright, then the next one is resonance effects. Now we've talked about resonance a little bit. In order to answer this, what I need you guys to understand is the structure of the conjugate base that we get out. We have an acid here. This is our hydrogen that's going to be removed, just as it is in this alcohol. So what I'm going to do is draw out the conjugate base of each of these 2 structures. So all I'm drawing here, that should be 2 dots rather than 1 line. All I'm doing here is drawing out the conjugate base of this acid. I remove the hydrogen and put that there. When I draw out the conjugate base of this guy, this is ethanol just above me, alright? Well, not just above me, but above this guy. When I put all the hydrogens on, what you'll see is that I have 2 conjugate bases here, both of which have a negative charge on the oxygen, this one and this one. We said on the last slide, acidity of an acid is solely dependent on how stable the conjugate base is that you get out. I've got these 2 conjugate bases, so the question really is, which of these 2 conjugate bases is the more stable? Is it this one or is it this one? Well, when we look at this one, we have this oxygen with the negative charge, the 3 lone pairs. You'll see there's nowhere for that negative charge to go. It's stuck on the oxygen. It's not particularly happy about it. Here, the negative charge is on the oxygen as well, but there is the option where I can funnel electrons into this bond, kick them up onto this oxygen, and draw out a second resonance structure for this conjugate base. Now, you've seen before, the more resonance structures you can draw, the more stable a particular structure is going to be. So what this means is when I draw out the other resonance structure, what this shows is that now I can move this negative charge from one oxygen to another, and it shuttles back and forth in a way that this one can't do. Therefore, this conjugate base is more stable, this guy is more acidic. Alright? So remember, whenever you're talking about acidity, the stability of the conjugate base is the most important thing to consider. Alright, last one here, hybridization effects. This is the simplest one to explain. And I have an alkyne, an alkene, and an alkane here. Triple bond, double bond, single bond between the two carbons. Now let's just do a bit of a refresher. What's the hybridization at each of these carbons? Well, on the triple bond, you have an sp hybridized carbon. For the double bond, you have an sp2 hybridized carbon. And for the single bond, you have an sp3 hybridized carbon. And again, we're going to look at the conjugate bases of each. Alright? In each case, I'm removing a hydrogen. I'm actually not going to draw out the products, but if I did, I'd have three sets of carbons with a lone pair and a negative charge on them. The fact is that the more bonds you have between your two carbons, the stronger of an acid your compound is going to be. That means that sp hybridized carbons are always the most acidic, sp2 are in the middle, and sp3 carbons are the least acidic. And you can get that from looking at the pKa's. The pKa of an alkyne is about 25. The pKa of an alkene like this is about 40, and the pKa of an alkane is going to be 50 plus. Strongest acid is the lowest pKa, and that is because when we look at the conjugate base with the triple bond there and the lone pair on that carbon after we remove that hydrogen, this sp hybridized carbon here is happier to hold the negative charge than this one or this one. Therefore, hybridization is important. sp hybridized carbons are more acidic than sp2 hybridized carbons, which are more acidic than sp3. So those are all the possible ways that compounds can be influenced in their acidity.